Okay, hello, my name is Shayan Majidi. I'll be doing a series of lectures on an introduction to building quantum computers. So let's get started. An overview of what the lectures are going to consist of. So we're going to start with some story time and go over how quantum computers came to be. Then we're going to look at how do you actually build one. So what are the components that you need to build a quantum computer? And then we're going to look at four quantum computers. So we're going to look at how do you do quantum computing with nuclear spin. So NMR quantum computing with light. We'll look at linear optical quantum computing with atoms. We'll look at particularly trapped ion quantum computing. And then with something we can think of as artificial atoms, also known as superconducting qubits, quantum computing. So this first video, I'll cover points 1 and 2. And then over the next two videos, I'll cover the four different types of quantum computers. So my favorite time, story time, part 1. So interestingly enough, the story of quantum computers actually begins with very little to do with quantum computing. Also, you'll notice by the sliding effects, I am a wizard with special effects. So please try to not be too impressed with my PowerPoint skills. So it begins with Gordon Moore. He was then Intel's CEO, and he made an observation. And he made this observation in the 1960s. And it was that the number of transistors per integrated circuit chip was doubling every 18 months. So who cares? Well, two reasons we care. One is that it's an incredibly impressive prediction that's held really well until as recently as last year. So here I have a plot of the transistor size. You might wonder, why am I saying transistor size? Moore's law is in terms of number of transistors. I'll get to that. And how I'm going to get to that is it's the other reason why Moore's law is really interesting. And that's because it has some interesting implications. So first is that, I mean, given that this is an engineering class, I'm probably preaching to the choir here, but when you double the number of transistors, you can think of that as doubling your computational power. And the other reason why it's interesting is that the size of the chips hasn't been growing. That's just because communication becomes difficult as if the chips become too large, like communication between transistors. So the way that Moore's law has been sustained is through the transistors halving in size. So that's how we get to this figure of transistors gradually getting smaller. I mean, maybe not gradually, like incredibly getting smaller. If you look at the most recent point I have there, that's 5 nanometers. And so 5 nanometers, to give you a sense of how big that is, your hair is 5,000 nanometers. So take 1,000 transistors, put them side by side, take your hair, and they'll equally as big. So he made this observation in the 1960s. Naturally, some questions follow. One question came up by Rolf Landauer. He was a researcher with IBM, and he asked sort of a natural question that, if transistors are shrinking, how far can we go? And he had one approach to answering this question that was interesting. He observed that computers erase information. So classical computers are, like computations are irreversible processes. I mean, to convince yourself of that, if I give you the inputs 2 and 3, and I tell you the operation's addition, you can get the answer is 5. If I tell you the output is 5 and the operation used was addition, there's infinitely many answers that get you to 5. So some information is being lost along the way through computation. Well, you're erasing information, so it's a decrease in entropy there. So the entropy must be increasing somewhere else to account for the second law of thermodynamics. And if you're a researcher, you want to go head to head with any law in physics, I mean, be my guest, the more ambitious the physical law you want to fight, the bigger, the more impressive maybe it is. But the one law you really never want to fight is the second law of thermodynamics. Like, pick a fight with anyone, don't fight with the law of entropy increasing. Rolf Landauer was a smart guy. He didn't fight it either. So if the entropy is increasing, where does it increase? Well, one way it can increase is through the generation of heat when the information is erased. So this is known as Landauers Principle, and there's plenty of papers experimentally testing this principle. So I encourage you, if you're interested, to look them up, or just, I mean, go to the Wikipedia page. There's plenty there. And so why is this a limit? Well, if you're generating heat in each transistor, and there's a certain amount of heat that has to be generated when you erase a bit of information. That means the more transistors you fit on a chip, the more heat is going to be produced per inch of that chip, or I mean, per whatever unit of, or I guess it should be square inch, per any unit of area you like. Don't really know why I used inch. I'm not American, and I mean, I love the metric system. But anyways, heat per square unit of area is going to increase. Why does that matter? Well, we have our transistor. That's what they look like, in case you didn't know. And if it's generating heat, we need to cool it down so it doesn't melt. But the more heat that's generated per unit of area, eventually it's going to get too hot that there's no cooling agent that's going to feasibly be able to cool the chip down to be able to allow the computer to operate. So he proposes this fundamental limit to how far we can shrink transistors. So it's an interesting proposal, and this proposal then spurred another question. And Charles H. Bennett, a researcher at IBM, was thinking of ways to overcome Landauer's limit. And he proposes that it could be done with reversible computing. And I mean, essentially the story is, if erasing information is what gives you the problem, let's just not erase any information. And you might think, well, that's going to be a pain. We're going to have to hold all this information as we go. But really, it's what he showed was that you can compute efficiently and reversibly. So you don't have to erase any information, and you don't need an unreasonable overhead of additional resources. So he says, okay, with reversible computing, we can overcome this limit. And that prompted a search for a reversible computation system, a method, or something that can do reversible computation. Well, Paul Benioff comes and he proposes that quantum computers would be reversible. The actions on quantum systems are unitary, they're reversible. So if we use a quantum system for computation, we can overcome Landauer's limit. But what he didn't realize at the time, or sorry, and just be more clear, so the way the computations work is by manipulating the system's Hamiltonian, a term that I now assume you're familiar with. But what he didn't realize at the time was the power of quantum computing. Like, suggesting quantum computers as a way to overcome this limit on transistor size is like discovering bubble wrap and like using it for wallpaper, which was actually the original use for bubble wrap. It was originally designed to be for wallpaper, but then people found a much more useful use for it, as we do with quantum computing. So Richard Feynman sort of gets credited as the first person to see the power of quantum computing. And this happened in the 1980s, so we're still sort of around the same time period. But what he had really sort of seen and proposed was the use of quantum computers for something called quantum simulation. So essentially what that is that we have systems that behave according to quantum mechanics. And these are complex systems, and their evolutions have incredibly many degrees of freedom. So determining something as simple as the ground state of caffeine molecule takes like a supercomputer to do. But if these systems were trying to simulate, if our computer was built from those systems, then we would be able to efficiently then simulate their interaction. So this is something that Feynman proposes. And that's a huge step forward, because there's an incredible amount of uses for quantum simulation. David Deutsch sort of then takes the sort of next and sort of final step to formalizing quantum computing. And he proposes a new class of problems that a quantum computer could solve more efficiently than a classical computer. And like, how much more efficiently? Like, if a quantum computer saves you 2 seconds on your calculation, yeah, big whoop. If it saves you many, many years on your calculation, okay, now we're talking. So David Deutsch comes and says, these new class of problems can exist. And he actually presents the first one, which is a quantum algorithm that can do things much more efficiently than a classical computer. So a general summary of what happened here is that first, More comes in and observes the transistors are shrinking. Then we have Landauer, who makes this comment that, okay, if they're shrinking, ask the question, they can only shrink so far because the computation is irreversible. Then Bennett proposes, well, okay, well, if the issue is irreversibility, let's find a reversible computer. Benioff proposes quantum systems. Feynman sees their use as quantum simulators. David Deutsch proposes quantum computers. So the six of them combine together and make the Megazord, which is quantum computing. So that's how we got to quantum computers. But what's happened since? Like, why do we have an institute for quantum computing? Why is there money in it? Why is someone paying me to be here to talk to you? Actually, no one's paying me to talk to you, but in theory, somebody could be paying me to talk to you because people care about quantum computing. Anyways, so advances since then. One big advance, and one that's being used currently, is the BB84 protocol. And in its name, it came out in 1984, and is used for quantum key distribution. Essentially, what is happening here is for you to securely send information to somebody else. Well, I'll say it like this. One way to securely send information to somebody else is with the use of an encryption key. So if you remember to passing notes in grade 2 or grade 3, I mean, I don't know if I'm showing my age by suggesting people still pass notes, or I don't know if kids young enough to text in grade 2 or grade 3. But if you're passing notes in grade 2 or grade 3, if you're smart, you don't just write out your message. You have some kind of encryption key. A means B, B means H, whatever, that only you and the other person knows. So those are great tools. But we need a way to remotely send those keys to one another. Because if we have to go and physically hand it to somebody else, like that's a pain. Fly across the world to send someone an encryption key, especially if you change your keys regularly for security. I mean, just not practical. So there's ways that you can use quantum systems to safely and remotely distribute keys. David Deutsch, which with Joza comes up with the first sort of superior algorithm. So the first algorithm that a quantum computer can do efficiently that a classical computer can't. It was just sort of a toy black box problem, but it showed that, hey, this class of problems does exist. What some people sort of then think of as the big bang of quantum computing was Shor's algorithm, and it came out in 1994. And the money bags there are, grossly under-exaggerating how much money this brought into quantum computing. What Shor essentially showed was that quantum computers could fill a blind spot in classical computers. So classical computers are good at lots of things, but they suck at a few things. One of them is taking a number and breaking it into its prime factors. So I mean, you give a computer 12, it breaks it into 2, 2, 3, fine. But if you give it a massive number and you ask it to break it into its prime factors, it struggles. What a quantum computer could do, though, is efficiently do such a factorization. Why does that matter? Well, the reason it matters is because classical computers are so bad at doing that, we take advantage of that blind spot to keep our internet information secure. So your bank PIN, messages you think you've privately sent to friends, all that stuff is kept safe and secure through exploiting the fact that classical computers can't factor prime numbers. Sort of speaking sort of fast and loose. Maybe I'm oversimplifying it a little bit, but you can see the significance of finding an algorithm that can do that. So if tomorrow I give you a quantum computer, you could steal my PIN and take all of my debt. I would love for you to do that. So those are sort of like some major advances so far. I'm going to throw out some future ones that aren't talked about so much. So if you pull up a paper on future applications of quantum computers, some sort of typical examples might come up: random number generators, I don't know, finding ground states of Hamiltonians. But just a couple applications that I think are sort of interesting is that ground state of Hamiltonian problem actually has profound implications in pharmaceuticals. So if you want to know how two things interact with one another, that's incredibly important in designing new drugs and medications. One way, or one thing that helps you determine how they're going to interact, is knowing the ground states of the Hamiltonians of those molecules. Quantum computers, or I mean, quantum simulators even, could do that much more efficiently than classical computers. So quantum computers will have a huge impact in drug design, or at least potentially could have a huge impact in drug design. Another one that's sort of interesting is that the processes to produce fertilizer take a lot of, need high pressure and high temperature environments, but some bacteria can produce the fertilizer at room temperature without any extra pressure. And determining how to do that is something that we could also get from studying the ground state of these molecules. So that's another way in which quantum computers could have applications to diverse fields. So implications in biochemistry. And really, etc. doesn't do it justice. If you go in the archive and you're regularly following, people's proposals and suggestions, the field is growing nonstop. Like since Shor's algorithm, the rate at which new papers are coming out in quantum computing, quantum information, with the different applications of quantum computing is just incredible. So it's really been taking off. And to prove that, I mean, just sort of look around the globe. If you look in academia, the number of institutions that have popped up with a focus on just quantum computing research is incredible. We have the Institute for Quantum Computing here. There's the Institute for Quantum Optics and Quantum Information in Austria, Center for Quantum Technology in Singapore. I mean, just search, quantum institutes. You're going to find a massive list of these institutes, and they are global. And then the industry is also there. So you have tech giants like Google, Intel, IBM, Microsoft, all of them with large and growing quantum computing, quantum information sectors, all sort of approaching this from different angles. And there's also many startups. In Waterloo, there's a few quantum computing startups or quantum information startups. So really the industry structures are there and they continue to grow. And then there's also national programs. So there's national research programs that have been created in Canada, China, European Union, Germany, US. Really any country with significant research resources has created national programs around quantum computing at this point. And so at this point, all this to say in another way, the people are there and the money is there. As an example, in Waterloo alone, there's been over $1.5 billion invested in quantum information in the last 20 years. So the money are there, the people are there, the infrastructure is there. Next question is, how do you build a quantum computer? Great question. This brings us to part 2. If you need a break, pause the video, go to the washroom, take a drink. If you're not sick of my voice yet, I'm going to keep going. Building a quantum computer, that's me. Those blocks are the pieces of my quantum computer. That's me building a quantum computer. So let's start sort of more basic. What is different about a quantum computer? Well, one is the qubit. And this came up in the last lecture that you had by John Donahue. So I'm not going to repeat what John shared because he is a much more eloquent speaker than I am, so I wouldn't do it justice. But I want to point out one example that I think really brings it home about the difference between a quantum bit and a classical bit. If I have 10 classical bits, those 10 classical bits, each of them is 0 or 1, can be in one of 2 to the 10, so 1,024 different states. If I have 10 qubits, they'll be in a complex superposition of all 1,024 different states. So for each of those states, there will be a distinct probability that's a complex, well, the probability is in a complex number. There'll be some complex number associated with each state, and that complex number can be used to determine the probability that it's in that state. So you have this much richer sort of space in which you can encode information in 10 qubits than 10 bits. So the qubit is sort of at the heart of it, but that's not the only thing that's sort of interesting. And that's the operations on them. So there's certain class of unitary operations which are very hard to simulate for a classical computer, but a quantum computer can simulate them efficiently. So for example, we have an operation that's acting on the 1,024 different probabilities. And each of the different operations, so you saw the circuit picture in John's lecture, that each of the elements of these circuits adjust all of those different probabilities. So what's the catch? Is 10 qubits not then like having a dual 1024 times processor? Well, no, that's because the catch is when you go to measure, you still only get one readout state. But we can still take advantage of that intermediary superposition before we take the measurement to do neat things, to do things that are impossible classically. So that's the difference. And then what are the pieces of a quantum computer? Like say, I don't know, I have some quantum system. I bring you some, I don't know, organic system. I come up with some leaves or something, and I say, I'm going to use these leaves to create a quantum computer. I don't mean to mock any example. There might even actually be quantum computers out there. People propose with biological systems. I don't know. But I'm saying if you come to me with your quantum system and you say, hey, I want to make a quantum computer out of this, well, what do you need to show that your system can do? There's 5 things. David DiVincenzo laid them out, I think it was the year 2000, maybe 2001. Oh, way off, 1996. Thank you, past Cheyenne, for correcting future Cheyenne. So in 1996, and the criteria consisted of a scalable physical system with well-characterized qubits. I'll explain each of these criteria in more detail, but the gist is you need your qubits. The ability to initialize the state of qubits to a simple fiducial state. You have to be, actually, again, I'll explain these all more in detail, but you need to be able to initialize it to some starting state, some equivalent to the all-zero state. You need a universal set of quantum gates, so you need to be able to act on the qubits. What's the point of an algorithm if you can't measure it? And then you need long relevant decoherence times. So I'll explain this too, but you need to be able to do your computation before all your quantum information is lost to the environment. So now I'll sort of just a little bit more detail on each of these. So this first criteria, a scalable physical system with well-characterized qubits, there's 2 parts to that statement. The first is, well, okay, I'll flip the order. The first is well-characterized. And what does that mean? That means it stays in the qubit subspace. So let's say I take an atom, and an atom has a ton of electronic states to it. It can be in this orbital, that orbital, like looking at those diagrams, you just get sick looking at how many different states it can be in. And I want to pick 2 of those states to make it my qubit. Great. Well, what if throughout my computation, it suddenly changes to some other state somewhere else? That's a problem. A well-characterized qubit stays in its subspace that we've defined as 0 and 1. And currently, we're pretty good at doing that. Most quantum systems, I say, I mean, that's not the problem keeping quantum computing experimentalists up at night. What's keeping them up at night regarding qubits is the second one, scalability. So you have to increase the number of qubits without experiencing serious loss in performance. This is the one right now that we're struggling with. Maybe struggling is too critical, but it's the bigger challenge. And right now there exists, for the most part, a trade-off with adding more qubits and the performance of those qubits. So with one extreme, you can have 3, 4 really, really good qubits that you can control really well. You can have them interact with other qubits, turn that interaction on and off instantly, measure them with high fidelity, prepare them in good states. But there's not much you can do with 3 or 4 qubits that's really that interesting anymore. It was interesting in the 90s and like early 2000s when people were working with them. But now it's not. And then you have the other end where you have like Google that had that report where they had 50 plus qubits. But then, you can question the quality of those qubits. Can they all interact with each other? How well can you control and measure each one? So that's the first criteria. And I think it's pretty intuitive. The qubits are your fundamental building block. Now, you need to be able to initialize the system. And really, that's just as simple as saying any output of an algorithm depends on its input. So if I don't know what my initial state is, I can't go in and do some algorithm on that or design some algorithm without knowing the initial state. Usually, we're going to come up with some initial state that we think of as the all zero state. Actually, we always think of it as the all zero state. And we need some kind of way to get our system into that all zero state. And so the third one then is the universal set of quantum gates. So we got our qubits, we've prepared them in the all zero state, now what? So John looked at quantum gates last lecture. So I won't spend too much time talking about them. But there's the classical example is the NAND gate, and you can use the NAND gate to create any classical algorithm you want. It's a universal gate. And then in quantum systems, there's many different gate sets that create a universal set of gates. But in general, you need at least 2 single qubit gates and 1 2-qubit gate. And if you remember sort of the picture of the block sphere from the last lecture as a sphere, so there's, with bits, you have 1 of 2 points describing the state of the bit. With a qubit, you have a whole sphere, and the points on that sphere, even inside the sphere, if you have decoherence, describe the state of the qubit. Well, to get from any point on the sphere to any other point, you need at least 2 angles, or at least 2 axes, of rotation. And if you want the qubits to interact with one another, you need at least 1 2-qubit gate that can create some entangling between the qubits. So you need a way to measure them. What's the point of having an algorithm in a quantum computer if you have no output? Generally, there's 2 ways to do measurements. One is with projective measurements. This is usually what you see in a textbook. It's a phenomenon that blows people's minds when they first see it, that you go to measure a quantum system, it's in this superposition, but when you measure it, it changes and it takes on one of the possible states. That's projective measurement, what you usually see when you're learning quantum mechanics. The other way is ensemble measurements. And so you can have many copies of sort of your quantum computer, and you can measure them all at once. And so instead of getting a projective measurement and returning one state, what you end up getting is a probability distribution of being in the different states. So those 4 criteria that I covered so far is everything you need for ideal quantum computing. So if our system was perfectly isolated from everything else, and our controls were absolutely perfect, there was no noise and no error in our controls, or our measurements were great. In reality, that's not the case. So quantum systems bleed quantum information to their environment. So they can begin in pure quantum states. This is what you are working with when you're writing out a ket. It's in some state with some complex number that determines the probability amplitude of being in either state. But as these qubits are allowed to interact with the environment, they become entangled with the environment, and some of their quantum information gets lost to the environment. This bleeding of quantum information is known as decoherence. So what you need then is a long relevant decoherence time. So you need a decoherence time that's much longer than your gate time. And really what that's saying is, if my decoherence time is, I don't know, 100 years, I can take a lot of time with my gates. My gates can take a few minutes and I'm okay. My decoherence time is a few seconds, then I need my gates to be crazy fast. So clearly there's 2 ways to meet this criteria. You increase your decoherence time, or you can decrease your gate time, or both. So you can decrease your gate time, but I mean, most, I think, attention, like maybe sometimes with some implementations, like we'll see with trapped ions, there probably still is more you can milk this, and you can decrease your gate times further. But with the other implementations, I think that the real focus is increasing decoherence time. And you just sort of do that by more carefully isolating your system from different sources of noise. Could be, for example, a stray electromagnetic field or thermal radiation in the environment. You just find better ways to isolate your system. So that was my quick crash course on how we got to quantum computing and how you build a quantum computer. I'll say that's about a third of the lecture. The next 2/3 are going to be looking at 4 types of quantum computers. and I'll get to those in the next video. If there's any questions you had about this first part, feel free to shoot me an email. If you want to discuss things, I have office hours for another course I do. And if no one's there, you can stop by. If people are there, we can set up another time to talk. I'm always happy to talk quantum. So thank you for listening, and I'll see you in the next part of the video.